Hi. So let's solve some more problems on Newton's laws of motion. All right. And these problems, as you can see, I have picked up these problems from your workbook. So let's see some problems from your workbook. All right. So the question over here is find the acceleration of each mass and tension in the string. All right. So I have to find the acceleration of each mass. Actually, look at the way the two masses are connected, right? The string bit that connects the two masses is taut, meaning it is tight, right? There is some tension in the string, right? And the string I'm going to assume to be inextensible. So the string will be assumed to be inextensible, meaning it cannot be. It's not like a rubber band, so it doesn't change its length. All right. Then what else do we assume? We assume that the string is uh, massless. We assume that the pulley is massless. This pulley over here is massless. And what else? And the surface over here is friction free. So we have friction free surface. The thread and the pulley are also friction free. So pulley is massless and friction free. All right. So these would be my assumptions in solving this problem. All right. So let's see. Like I said, I asked you to look at the system over here. So if you look at the system over here, you can see that the masses, 5 kg mass and the 10 kg mass, are interrelated in such way, interconnected in such way that if the displacement of the 5 kg mass is x, the displacement of the 10 kg mass also will be x. If I pull the 5 kg mass by x, the 10 kg mass also would move by the same amount x. All right, kind of obvious, isn't it? So if I say that the acceleration of a 5 kg mass is a, then the acceleration of the 10 kg mass is also a. I hope that makes sense. Displacement divided by time would be velocity. Velocity by time would be acceleration. Since the displacement is same in either cases, so displacement undergone by the body in time t for the 5 kg body and displacement undergone by the 10 kg body in the same time t would be same, right? So the velocities would be same, and similarly accelerations also would be same, right? This is how they are connected. That's how they are connected. There is no bigger reason than that. All right. So let's see. Now what are we going to do? I'm going to apply uh, Newton's laws to these masses. So let me apply Newton's law to the 5 kg mass. So here's my 5 kg mass. I'm just considering the 5 kg mass. So I hope you understand how Newton's laws work. Newton says, suppose I give you an object. I give you an object of certain mass m, and you push it or pull it. You give a force to this. You apply a force on this object, and once I know the force acting on the object, I can figure out how it's moving. That is Newton's law. All right. So I want to find how the 5 kg mass is moving. So for that purpose, what I'll do is I'll figure out the forces acting on this body. So if I know the forces acting on the body, I can figure out everything else about the body, right? What its acceleration is, where will it be after 2 seconds, right? And what will its speed be after 2 seconds, and all those things can be figured out from Newton's laws. So the first step would be to figure out the forces acting on the body. So here's the 5 kg body. So let me just draw the forces. Now, how the force is applied to the body is not relevant. Newton doesn't say anything about how you should apply the forces. He just says you apply a force, okay, then the acceleration will be given by force divided by mass, unbalanced force divided by mass. How you apply the force is irrelevant, right? So if you want the earth to go around the sun, right, you could, and just a wild imagination, my wild imagination, you could tie a thread to the earth and let it go around, right? That also would make the earth go around the sun, right? And of course, gravity is the force that makes earth go around the sun. So what exactly the force is, the agent responsible, sorry, kind of force is not relevant. Only that the force, what the force is, the magnitude and the direction of the force, only that thing is important to figure out the motion of the object. Okay, so it could be the tension in the thread, or it could be gravitational force, or it could be electrostatic force that you might have studied. So you could have two charges over here. You could hold the bodies by two charges, to keep two unlike charges that would hold the bodies together. That is also a valid way of doing it. Or you could have magnets. So no matter what the force is, what kind of force it is, it doesn't matter. So as long as there is a force, that force would cause an acceleration in the body. And acceleration, after once you know the acceleration, you can figure out velocity and displacement as well. All right. So here's my 5 kg mass. So let me identify the forces acting on this body. This we have to do. We have to identify what are the forces acting on the body. Okay. So I see that the 5 kg mass is connected to a thread over here. All right. So the thread, as you can see, if you look at the join of the 5 kg mass to the thread, if you look at the join of the 5 kg mass to the thread, this is the common point on the thread as well as the mass. Suppose there is a knot over there. What's happening at the knot, right? So if I zoom it further, I can see that the molecules of the 5 kg mass and the molecules of the rope molecules are holding each other up, right? So any object is just bunch of molecules, right? So here you can see that these molecules are the ones that are holding the 5 kg mass up, right? So what force, with what force do they hold each other up? So that whatever that force is, we say that force be called as the tension. So here's the point on the 5 kg mass, that point is being pulled up by another point over here. Okay, and whatever that force is, whatever that force that is pulling it up, that force we call as the tensional force. So tensional forces arise because of molecular interactions. All right. So of course, Newton, when he did all this, he did not know that there are molecules and all those things. He just said, okay, we have a thread, we have a rope, and rope can exert a tensional force. That's all he said. And that's good enough. All right. And that's good enough for us also. But now we have a deeper understanding of what rope is made of, what masses are made of. So we can go a step further than Newton could and see what's exactly happening. All right. So here's the 5 kg mass, and like I said, there is a tensional force acting on that 5 kg mass. All right. So there's some force T acting on the 5 kg mass. That's in the upward direction. This force is trying to pull it upward. And then there is a downward force of the downward force, and this downward force is the weight of the object. So in the previous section, you have studied that every object is pulled down to the earth with an acceleration due to gravity g. No matter what the mass is, all objects try to accelerate downward at the rate g, right? So if you are trying to, if I take this particular pencil over here, so if this pencil, if I were to leave it, if it were to go down with an acceleration g, what should be the force acting on it? See, what I hope you understood my question. Here's the pencil. I leave it. All right. Then I know that if I leave it, it accelerates at the uniform rate of g. Right. So an object accelerates downward with a uniform rate of g. Now you know that any acceleration must be caused by a force. So let's call this force as the weight of the object. So let's say this is the weight of the object. Weight is a force. So weight of the object. So acceleration due to gravity. So acceleration G is equal to the force acting on the body divided by the mass of the body. So I'm interested in the force here. So weight or the force acting on the body is equal to mass times acceleration due to gravity. mg. Whatever the mass is, the weight would be m into g. That mass into g. If you have 10 kg mass, then it would be 10g. All right, that's the weight. So here the mass is 5 kg. Sorry, the mass is 5 kg, and therefore the weight would be 5 times g, m into g. That's the weight. All right. So I have identified all the forces that are acting on that 5 kg mass. All right. Now I have to be a little bit careful over here. What do I mean by all the forces? What I mean by all the forces is all the external forces. That is very important. Like I said just now, that if you take 5 kg mass, I just told you that there are molecules inside. There are molecules that are holding up, that are making up this 5 kg mass, isn't it? And you have studied already that there are intermolecular forces. So there are forces over here that are holding these molecules together, right? There are molecules in me, and there are intermolecular forces that are acting between those molecules, and these molecules are not causing me to move. So here's my water bottle. So you can see that there are a bunch of molecules over here. Of course, you can't see the molecules, but you know that there are molecules, and there are intermolecular forces. How do I know that there are intermolecular forces? So if I press the bottle like that, I can feel that there is something pressing against my thumb. What is that? Where is that force coming from? So you could argue that I'm pressing on the bottle, right? And you can see that the bottle compresses a little bit and then it comes back. So what is bringing it back? So what compressed is my muscular strength. What is bringing it back? So there are intermolecular forces there. And you can see, even though that there are intermolecular forces, this bottle will not move anywhere, will not accelerate, right? So what's happening here? What is the reason for this? Well, Newton never said that just because there are forces, an object would move. All right. If you recall Newton's first law, every object continues to stay at rest or continues to move with uniform velocity until or unless acted upon by an external, this is important, external unbalanced forces. So the forces have to be external to the object. Okay, the internal forces do not make the object move on the whole. So the forces have to be external to the object. So here's a 5 kg object, and the forces that are external to the object are the weight of the object and the tension in the rope. So tension is an external force that's coming because of the rope. All right. So that's important. And what's happening because of these external unbalanced forces? Okay, so I can see that this object over here would be accelerating downward with an acceleration A. Notice that I'm just calling it A. I do not know what its value is. I'm saying, okay, there are unbalanced forces, there are external unbalanced forces, therefore there must be some acceleration due to Newton's law, right? What that acceleration is, I do not know, right? I do not know what this value of acceleration is. I'm saying there is some acceleration. Let's call it as A. Okay, that's what we have chosen to do now. So let me write that over here. A What might A be? A is equal to, you can see that I have indicated the direction of A to be downward, and that's kind of obvious, isn't it? So look at the system again. Look at the system again. So you've got a slippery surface over here on which you've kept a 10 kg mass, and then you have connected that 10 kg mass through a thread over a pulley and to a 5 kg mass like that, which is hanging. All right. So obviously the 5 kg mass would come down, isn't it? Bringing the 10 kg mass along with it. Right. So my choice of direction of acceleration is not completely random. Uh, it is reasonable. All right. Now, even if I get it wrong, even if I even if I say I am completely new to this, I don't have any intuition. So if I randomly mark it as upward, let's say acceleration is upward, nothing will go wrong. You'll get the negative sign at the end. Okay. You'll get a negative sign at the end, which you'll have to interpret as opposite to your assumed positive direction. All right. So nothing would go wrong, but it's best to write the proper directions by using your intuition. All right. So A is downward. Now A is downward, meaning that the force of the weight is larger than the force of tension. Right. If the downward force is larger than the upward force, then the acceleration would be downward, isn't it? So acceleration should be downward. So what is the net force acting on the object? The net force acting on the object, why am I interested in net force? Because acceleration of the object is equal to the net unbalanced force acting on the body divided by the mass of the body. So F net over here is 5g, that's the downward force, minus the upward force, which is the tension, divided by the mass. And this is our equation. So mass is, I forgot to write, mass is 5 kg. Let's write it right here. So mass is 5 kg. Let's put that there. Okay. So as you can see, I have figured out every detail here. I know that the acceleration is 5g minus t divided by 5, whatever that is. So have I really figured out the answer? That's the question that I'm trying to ask. The answer is no, I haven't really figured out the answer, because figuring out the answer means what? I should know the final answer, final value. Acceleration is 2 meter per second or 3 meter per second. Do we know that? Actually, no. See, this is all right. 5g is all right because I know the g value. 5 into g would be 50. So 50 minus something, we do not know what that something is, right? So if we knew the tension in the string, everything is figured out. Acceleration would be known to us, but we do not know the tension, and that's the next part of the problem, to figure out the tension value. All right. So how do we figure out the tension value? Now you can see that I've applied the Newton's equations for the 5 kg mass. So it's already done. Whatever the 5 kg mass, whatever information that the 5 kg mass could offer, it has already offered. There is nothing more to be done with the 5 kg mass. So we can't get any new information from the 5 kg mass. So we'll have to look elsewhere. So where do we look? So we'll be looking at the 10 kg mass. So let's see what's happening here at the 10 kg mass. So tension in the rope, it's a massless rope, right? So massless rope means what? Massless rope means the tension throughout the rope must be same. Why is that the case? So I can apply Newton's law to anything over here. So let me apply Newton's law to this section of the rope. I'm taking a small section of the rope, which is over here. And let me write that over here. So here's the section of the rope. What is the acceleration of the section of the rope? Strange question. What is the acceleration of that section of the rope? Or in other words, what is the acceleration of each of the sections that you can imagine over here? So what is their acceleration? uh, you know that the masses are themselves accelerating at a, right? If the masses are accelerating at a and the string is tight, right? If the string is tight, then each section would also be accelerating at the rate a, right? So the acceleration of this part of the string is also a. Now how is it accelerating, right? So there must be some force acting on it, but let's see what those forces are. I i told you there is tension in the rope, isn't it? So I can draw a tensional force like that. This is the tensional force T, and then I will draw a tensional force over here, and I'll call that tension T as well. Both the tensional force, both the sides, I'm calling the tension as T. Now why do I do that? Because I know this section of the rope is massless. This is a massless rope, isn't it? Now, if it's a massless rope, and if there is any unbalanced force, if there is any unbalanced force acting on that massless rope, what would happen? So, acceleration, let's say there is some unbalanced force, some F unbalanced force, divided by mass of the rope is 0. So you find that acceleration would be infinite. So if you imagine something that is massless and there is some unbalanced force on that massless object, it would have infinite acceleration. Okay, which is completely unreasonable, because I know that the section of the rope is not accelerating infinitely, it is accelerating at a finite rate of a. So its acceleration is a. So what's the only possibility? So only possibility is the net force acting on that section of the rope is also 0. So 0 by 0 can be anything, right? So acceleration of that rope is 0 by 0. 0 by 0 is what? 0 by 0 can be anything. In this case, what is it? In this case, it is equal to the acceleration A itself. What is A? A is the acceleration of the mass. All right. So what I just proved is that the tension at every section, tensional force in every section of the rope is same. All right. So if the tensional force here I called as T, so I'd call the tensional force here as T. So this was T. The tensional force here would also be equal to T, the same argument, right? So there is a tensional force acting on that 10 kg mass. So let me draw the free body diagram for the 10 kg mass. So here's my 10 kg mass. So here's the 10 kg mass, and it's kept on a surface. It's kept on a surface. So identify the forces acting on this 10 kg mass. So you can see that the 10 kg mass, every object has weight. So weight of a 10 kg mass would be always downward, and its weight is 10 g, right? But it's kept on a floor, friction free floor, right? So the floor would offer a normal force. The floor would offer a normal force N. What else? What other forces are acting on this? Well, there is the tension T acting on the object. So are there any other external forces? I don't think so. These are all the external forces acting on the object. Now, how is the body moving? You have to use an imagination over here. How is the 10 kg mass moving? Is it jumping up? Is it going up the floor? No, it does not accelerate upward. It does not accelerate upward means what? The force is a vector, right? So you can use Galileo's law now. So if there is no acceleration along the upward direction, if there is no force along the upward direction, then the acceleration in the upward direction would be 0, right? So acceleration, since I know that acceleration in the upward direction is 0, right, because it's not jumping up and down. So what do I conclude from that? So acceleration along the upward direction is 0, but what is the acceleration equal to? Acceleration is equal to the forces in that direction. So here I'm talking about the y direction. So y acceleration along the y direction is caused by forces that are acting along the y direction only. X direction forces do not affect y direction motion, right? So what are the y direction forces? Well, there is a normal force which is acting upward minus the weight which is acting downward. So these are the net forces in the y direction, divided by the mass of the object, which is 10. And as you can see, I have said that acceleration along the y direction is 0. How did I say that? By observation. Okay, the object doesn't move upward, isn't it? So acceleration is obviously 0. What does that imply? So 0 is equal to n minus 10g divided by 10. 10 you take to the other side, so you'll get 0 there. So you have n is equal to 10g. You see, these two forces are balanced. N is equal to 10g means what? That the vertical forces are balanced. So balanced forces do not affect the motion of the body, do not affect the state of the motion of the body, right? But they do not affect the state of the motion of the body in that direction. So these are vertical forces. So along the vertical direction, there is no state of motion. So Newton's law is valid. Newton's first law is true in the vertical direction. What did that say? Every body continues to stay at rest or continues to move with uniform velocity unless acted upon by external unbalanced forces. So here we see that there are no external unbalanced forces in the vertical direction. So in the vertical direction, the body will continue to stay at rest. Okay, so no vertical motion, continues to stay at rest because it was initially at rest, isn't it? So it will continue to stay at rest in the vertical direction. What about the horizontal direction? Well, in the horizontal direction, I have, let me draw that over here again. So here's my 10 kg mass. In the horizontal direction, there's a force T. There's a tensional force T. And I've already identified what is the acceleration of the 10 kg mass. Well, the acceleration of the 10 kg mass is same as the acceleration of the 5 kg mass, which is A itself. Alright, so same acceleration. So acceleration is A. Alright, so let's write Newton's law for this. So acceleration is equal to the net force acting on the body, which is the tension, divided by the mass of the body, which is 10. So from here, I get that T is equal to 10 times A. And this would be my second equation. Let me number it. This is the second equation and here's the first equation. All right, let's just look at these equations now. All right, you see, you might think that this is a really long problem. It's not. You can see that I have not written much. It's just that I've spoken a lot because I'm trying to guide you through the problem. So once you understand the problem, you can do it in 2 minutes, under 2 minutes. I guarantee you that. All right, so 5g minus t divided by 5, that's the first equation. And the problem that we had with the first equation was we did not know tension, right? If we knew tension, then I had told you that we would have figured out acceleration. So tension we did not know. Now you see that second equation tells me that the tension, whatever the tension is equal to 10 times 10 into A. So let's plug those two equations together. So let's see. So the first equation says that A is equal to 5g minus t. Okay, let me take this 5 to the other side. So this becomes 5a is equal to 5g minus t. The second equation says that 10a, right? I'm looking at it the other way. So 10a is equal to t. 10a is equal to t. This is the first equation, and this is the second equation. Okay. So 5a is equal to 5g minus t. 10a is equal to t. Can we simplify this problem further? Let's see. So what if I multiply the first? You are free to do it your own way. Try it out. All right. What's the easiest thing to do would be to substitute t over here. All right. So plug in the value of t. So 5a is equal to 5g minus t, but t is 10a. Right. You bring 10a to this side. So that would be 15a is equal to 5g. All right, I think I figured out the answer, isn't it? A is equal to 5 by 15g, or 1/3 of g. So A is equal to 1/3 of g, or A is equal to, now we get a number, 10 by 3. 10 by 3 meter per second per second. That's our answer. Okay, and I told you that we can figure out other information as well, isn't it? It's not asked in the question over here, but let's ask that question anyway. So if the 5 kg mass is starting from rest, if it's starting from rest, meaning its initial speed is 0, how fast would it be moving in 2 seconds? All right. So let's say that this distance is long enough so that the 10 kg mass does not strike the pulley over here. This 10 kg mass does not strike the pulley over here within 2 seconds. That's otherwise then the situation changes, right? Because now the forces are different. Pulley would be offering a force, and all the equations that I've written down will not be valid. All right, all these equations are valid based on the assumption that only force acting on the 10 kg mass is the tensional force. All right, if it strikes the pulley, then that situation would change, which would imply that my equations will not hold true when that happens. All right, so let's assume that in 2 seconds the 10 kg mass does not strike the pulley. So what is the speed of the 5 kg mass in 2 seconds? How do we do that? Well, I know the acceleration of the 2 kg mass. Acceleration of the 2 kg mass is 10 by 3. So, and it's a constant acceleration. Acceleration is constant, which means that I can apply the kinematic equation, which is v is equal to u plus 8. So v is what I need to find. U is 0 plus a is 10 by 3 into 2 seconds. So speed will be 20 by 3 meter per second. Okay, it's going quite fast actually. Right, 20 by 3 meter per second. How far has it moved in 2 seconds? Well, that you can find using S is equal to ut plus half at square. So the displacement of the mass, ut is 0, u is 0, right? So plus half into a is 10 by 3 into t square is 2 into 2. So one of the 2's get cancelled, and displacement also is equal to 20 by 3 meter. All right, so look at the information that we have found out. What else can we find out? What is the kinetic energy? Can we find the kinetic energy of the system? Yes, we can find the kinetic energy. Can we find the potential energy? Yes. You have not learned these topics, but yes, you can do that. All right. So that's the benefit of Newton's laws. Once you know the forces, if you know the forces, and if you know how to work with these forces, you can figure out everything else about the system. All right. Yes. So let's solve one more problem of the of similar kind, but there is a small difference over here. Here we are going to include friction. So you can see that this is almost similar to the previous problem, but friction is included. So friction is present only on this surface over here. So there is friction on this surface. So there is no friction on the pulley and the thread. So how do we deal with such a problem? So I'm not going to explain more about this. I'm just going to include the frictional force. So let me draw the free body diagram for this 50 kg mass. So here's the 50 kg mass, right? So this is 50 kgs. What are the forces acting on the 50 kg mass? So the forces acting on the 50 kg mass are its own weight. So its own weight, which is 50g. 50g is the weight of the 50 kg mass, and there is tensional force T acting on it. And let's say that the 50 kg mass moves down with an acceleration of A. So let's say that the 50 kg mass moves down with an acceleration A. So let's write that as A. So 50 kg mass is moving downward with an acceleration A. So what is this A equal to? A is equal to 50g, the downward force, which is the weight, minus the tension divided by the mass of the object, which is 50. So F net divided by m, that's the acceleration. So I can write this as 50 into A is equal to 50g minus the tension. Alright. See, you see that the problem is similar now. So if you want to find the acceleration, you see that you do not know the tension. Right? All problems, most of the problems, once you solve enough problems, you see similarities between the problems. So I do not know the tension over here. So how do I find tension? So to find the tension, I'd go to the 10 kg mass. So let me write the free body diagram for the 10 kg mass. So I can see that the 10 kg mass, what are the forces? I'm going to ignore the vertical forces. We have seen in the previous class that, previous section, we have seen it in the previous section that the vertical forces do not accelerate the mass, right? So why write them? There is no motion along the vertical. So I'm just going to consider the horizontal forces only. So horizontal forces are tension in the string, that is T. So if this tension is T, then the tension over here is also T, right? What else? What else? So here there is frictional force, right? Now the body is trying to accelerate in that direction with an acceleration A. So you can try this. So if you're trying to accelerate in one direction, what is the frictional force? Which way is the frictional force experienced? Frictional force is always in the direction opposing the motion. You've learned this, isn't it? So frictional force is always in the direction opposing the motion. So since the motion is in this direction, the frictional force would be opposing the motion. And what is the value of the frictional force? Frictional force is equal to mu, which is given, times n, which is the normal force, right? Now I need to find the normal force. What is the normal force? To find the normal force, I'd have to draw the diagram over here. What is the normal force? So like I said, the body doesn't move in the vertical direction. So what are the forces? So downward force is 10g and the normal force is n. Since the body doesn't move in the vertical direction, the vertical forces must be balanced. So n should be equal to 10g, right? So I get my frictional force is equal to mu is zero point 0.4 into 10g, that is frictional force is 4g. That's the frictional force. All right, so let's write the Newton's law for this 10 kg mass. So I see that the 10 kg mass moves in the direction of the tension. So let me write the equations. So A is equal to acceleration of the 10 kg mass is equal to the tension in the string minus the frictional force, which is 4g, divided by the mass of the object, which in this case is 10. So I can write 10A is equal to 10 minus 4, sorry, t minus 4g. So this would be my second equation. I've already written down my first equation over here. You see that this Newton's law problem, finding acceleration and tension, has boiled down to the problem that you have already solved in your 9th standard or 8th standard, simultaneous linear equations, isn't it? So you have to solve simultaneously these two linear equations and you'll get your answer. All right, so what would be the strategy here? So you can see that in the equation 1 you have 50a, and in the equation 2 you have 10a. So first you multiply throughout the second equation by 5. So you will get 50a is equal to 5t minus 20g. Nothing has changed. I've multiplied throughout, so by 5. So that's like multiplying by 1, isn't it? So not changed the equation, not changed any information contained in the equation. So 50a is equal to 5t minus 20g. All right, now let's subtract equation 2 from equation 1. Sorry, I'm saying it the other way around. I always get confused with this. So let me subtract equation 2 from equation 1. All right, so what do we get? So equation 1 says 50a is equal to 50g minus t, right? So minus the second equation. So second equation is this minus, so I'm subtracting, right? So minus second equation, the left hand side is 50a is equal to what? 5t minus 20g. So I'm subtracting. Just remember that there is a negative sign there. So 50a minus 50a, that is 0. T minus 5t. So this is t minus 5t, that is minus 6t. And then there is 20g minus 20, sorry, 50g minus of minus 20g, which is plus 70g. So from here I get that 6t is equal to 70g, or t is equal to 70g by 6. Okay, so we found the tension. That was the problem here, isn't it? I did not know the tension to figure out the acceleration. So I have two options. One thing is I can use equation 1 to figure out acceleration, or equation 2 to figure out the acceleration. So whichever one is easy. I think equation 2 would be easier, right? It's a choice that I'm making there. Let me use equation 2. So 10a is equal to t, which is 70g divided by 6. minus 4g. Okay, so 10a is equal to 70g by 6 minus 4g. Now you can subtract two quantities only if the denominators are same, isn't it? So let's make the denominator same. How do you make the denominator same without changing the value? You multiply and divide by the same number, meaning multiply by 1 basically. If you multiply by 1, the number doesn't change, isn't it? So, but I write this one a bit differently. I write it as 6 by 6. I write it as 6 by 6. 6 by 6 is 1. So I'm multiplying 4g by 1, not changing the value, right? But what happened here? So 70g minus, what is the numerator? Numerator is 24g, but both of them have the same denominators now, right? So I can subtract the numerators. So 70g minus 24g. So 70 minus 20 would be 50. 50 minus 4 would be 46. 46g divided by 6. And this is equal to 10a. So a is equal to 46g divided by 60. And this is your answer. You can simplify it if you want. You can go further and simplify. I see that it goes in the table of 2. But for me, this is good enough. Alright, I'll stop here. Yes, let's look at one more question of a similar kind. So refer to the figure. The pulleys and the string are light, and also assume that they're friction free, not mentioned over here. T is the tension in the string. So there is tension in the string, which is T. So there's tension here, which is T. There's tension over here, which is T. Yes. Which of the following are correct? The acceleration of the system is 5 meter per second per second. Tension is equal to 0 Newton. The acceleration of the system is 10 meter per second per second. Now, I'd like to immediately rule out one option. I don't think option B is correct at all. Right? I have not solved any equations. I have not done any equations. I have not solved any equations. But I feel that option B cannot be correct. Now, what's my basis for this argument? Now, just look at that. You are hanging something over here, which is a 1 kg mass. Just imagine this. And a thread goes over a pulley onto another pulley and then finally onto another mass 1 kg there. Right? Do you really think that there wouldn't be a tension in the string? Would the string be very loose? Right? Tension is equal to 0 means what? There is no you can easily move the string. Right? So do you think that would be true? I don't think so. Then tension is equal to 0 Newton might not be correct. All right. I am fairly certain that it is not correct. All right. So how do we solve these equations then? So let's see. So there is, I'm going to apply the free body diagram to this mass A. So mass A, let's see, accelerates downward with an acceleration g. So the weight is equal to 1g or simply g, 1g. Okay. It accelerates downward. So let's say that the acceleration is some a. Same story again. All right. Now just look at this system over here. So the thread goes over the pulley. What does the pulley do? What is the action of the pulley? Pulley just redirects tension. Right? It changes the direction of the tension. So tension is acting downward now, right, at the pulley. And pulley, what it does is it changes the direction of the tension. That's all it does. That's the action of the pulley. So if you're trying to pull water from a well, you tie a rope, let it go around the pulley, and you pull downward. But the pot that you have kept there inside the well feels a force upward. So you're pulling downward, but the force experience is upward. And what device did that job? That's the pulley, right? So pulley kind of redirects the tension. So that's what this pulley is over here is doing as well. So the tension direction is changed now, and this pulley again changes the direction of the tension. And here we are. Okay, so let's see. What is the acceleration of this 1 kg mass? So this 1 kg mass, as you can see again, the same arguments hold. If the first 1 kg mass, if the mass A moves down by 1 meter, the mass B over here, this mass also moves by 1 meter because of the way they are connected. So if this acceleration I call as A, I will be forced to call this also as A, right? So both the accelerations are A. Okay, so let's see what happens. So acceleration is equal to, let's see, acceleration is equal to 1g minus t divided by 1, or A is equal to g minus t. A is equal to g minus t, isn't it? That's the first equation. This equation I obtained from applying Newton's laws to body number A. So for body B, let's do the same thing. For body B, what is the force? What is the acceleration? Acceleration is same, A. What is the force acting on this body? T. The net force acting on the body is T. Unbalanced force is T. There are other forces which I'm ignoring, weight and the normal force. So T divided by the mass of the object, which is 1. So what do I get here? I get that A is equal to T. That's the second equation. This is for body B. So A is equal to T. Alright, plug it in the first equation there. So A is equal to G minus T, but T is numerically equal to A itself. So put that. Take A to the other side, you'll have 2A is equal to G and A is equal to G by 2. A is equal to G by 2. Alright, G by 2 means what? A is equal to G is 10. So 10 by 2. So 5 meter per second per second. And what is the tension? Tension is numerically equal to the acceleration value. So tension is equal to A. Tension is not equal to A. Don't get me wrong there. Tension is a force. A is an acceleration. That's why I keep saying numerically equal to. So T is equal to A Newton. So 5 Newton. T is equal to 5 Newton. You see, I was right. Tension cannot be equal to 0. Tension is equal to 5 Newton. So which are the correct statements here? So correct statements here, there is only one correct statement. This one. The acceleration of the system is 5 meter per second. Sorry, 5 meter per second per second. There is one more thing that I'd like you to notice. So in this case, we have found the acceleration of the system to be equal to, let's see, g by the sum of the masses, isn't it? 1 plus 1. That is 2. Acceleration is g by 2. Let me go to the previous problems. So not with the friction, the other one. What is the acceleration that we found over here? What is the acceleration? We found the acceleration to be equal to g by 3. Acceleration is equal to g by 3. Do you notice any sort of pattern over here? In this case, acceleration is equal to g by 3. Alright. In the first problem that we solved. And in the last problem that we solved, acceleration is equal to g by 2. So can you think of what's happening over here? Is there a pattern, or is it just it doesn't look like there is a pattern? One is g by 2, another one is g by 3. Do you see how to link them? Try to find out a pattern. Try one more example of similar kind. Okay, take different values and see what the answer you get, and try to reason out why you get that answer. Okay, this I'll leave to you. Yes, thank you.